Okay, in this section, we want to continue talking about probability, but we've got some harder ideas. Today's main idea is one called conditional probabilities. And over the years, as I've tried to wrap my head around it, the best way I can understand it is by thinking of this as a series of events in time. Let me show you what I mean. So I've got two airlines here, if I can get my pen to write. Okay, let's see if this works. All right, we've got two airlines here. One is Delta and one is United. Okay, and you first select an airline. When you go to this airport, there's only two. I don't know why, but there's only two choices. So then you're going to take a look and see if your flight is on time or if it's late. So you see my little tree diagram here. I've got on time, late. So this is a series in time. You first make this choice, and then this second set of branches, you make the second choice. I'm totally just making up percentages here, if my pen will write. Okay, this time I make it up, and Delta's a little better than United. Sometimes it changes. Okay, so this second column here is a conditional probability. It depends on something previous already happening in time, and what has already happened in time is you've picked an airline. So for instance, what I'm saying is this. The probability, this is a conditional probability. What's behind the line is what has already taken place in time. You have already selected Delta Airlines, and we want to know the probability that you're on time, but it's given that this has occurred. Well, that's what this column is. It's always the conditional choices, okay? It's a singular event. It's not multiple things. It's one singular event in time, and it's that based on the fact that what happened in round one has already occurred. So the probability of being on time, given that you've chosen Delta Airlines, is 85%, 0.85. It's just this spot right here. First, we chose Delta, and then we were on time. Now, we want to talk about and probabilities this time, but let's review last time we talked about or. Or probabilities are this. I'm happy if my spinner lands on the green space or if it lands on the red space. So my chances have improved. So with or, what we do is we add. Probabilities are really fractions, like success over total. So if I add fractions, things are getting better, which is what you should expect with or. I'm happy with either one, so I'm happy lots of ways. And, however, is multiplication. And is the idea that I need two things to happen. First this one, then that one. So if I need both things to occur, two things had to happen. It's harder to make two things happen. And so if you think about fractions, if you are multiplying fractions 1/3 times 1/4, it's now 1/12. It was harder to get both of those things to happen at the same time. Okay, so let's back to our airlines here. When you make a tree diagram like this, come and finish the and column. Okay, the and column is two things happening. You follow each branch. You start with delta, go to on time, and you multiply those two things together. 0.55, 0.85. That's both of them. A conditional probability is not two things. It's one thing. The first was the choice of an airline. That was a thing. The on time or late, that's the second. If you want them both to be true, delta and on time, you have to multiply them together. And whatever you get there is your and. So you go down and do 0.55 times 0.15, 0.45 times 0.82, 0.45 times 0.18. You get all of these and choices. Okay? Now, this is called the general multiplication rule. It just means this. Go down the tree branch. Here's the first thing that happened, and here's the second, given that that already happened. That was the branch. That's what we did. We went here, and then we went down there. Okay, now in order to understand the next screen, you got to understand this idea called independent events. And the root idea is this. I should say it like this. I want to know the probability of getting flipping heads on a coin, given the fact that lightning just struck in the field across from us. So if you think about that for a minute, so what happened first is lightning struck, okay? Great, that's what this means. The line means something has happened in the past. Lightning struck. Now, what's the chance of getting a heads? It's the same. It's the same as it always is. It's 0.5. Nothing has changed. And so this is meaningless in this story. Lightning striking, a meteor falling out of the sky, whatever it is, it had no impact whatsoever on this thing that has occurred. And the only way to prove whether something is independent is mathematical. You have to see if the probability of getting a heads is the probability of getting a heads whether something else happened. If these are the same, then you have independent events. If what happened first behind the line had no bearing on this, then they would be the same, and those are called independent events. If what happened behind this line has changed the probability of this one, those are dependent events. Okay, now look again. Here's another version of the multiplication rule. The only thing that's different is it's for independent events. But look, what we just said? If lightning has nothing to do with it, you get the same thing. So if you have independent events, there's no need for whatever line there is here. So the probability of B given A is just the probability of B. A had nothing to do with it. So instead of, this is not a whole nother formula. All it is because they're independent, we can get rid of this, but we don't need the line there. It doesn't mean anything. So we just drop it and we can just multiply the two together. Okay, there they are again. All right, we got a couple more ideas and then we're done. Let's talk about replacement. If I wanted to find, great, I give you a set of cards and I want you to pick an ace. Remember, there's 52 cards in a deck. There's 4 aces in there. So the probability of getting an ace, the successes over the total, is 4 over 52, right? You agree with that? What if I said, though, I want you to pick a second ace. I want you to pick 2 aces in a row. Now, it makes a big difference whether you replace something or whether you don't. What I mean is this. If you put the card back in, okay, that's what we're going to talk about first. You draw an ace, you put the ace back in. This is what it would take to get 2 aces in a row. You drew an ace. Now you got to do it again, multiplication. Okay? But let's suppose you didn't put the card back in. You got an ace, but you set that ace down on the table. Do you see now that there are only 3 aces left? So you only have 3 chances of getting another one. And because you have a card also removed, there's only 51 cards left. That's not a comma, that's a multiplication. One of these is independent and one is dependent. Do you see that this one, what happened first when we left the card on the table, has impacted the second? It has changed the probability of getting the second ace. Do you see? So this is dependent. This happened, changed the second probability. But up here it's independent. We put the card back in, we replaced it. And so that had no bearing on the fact it's still the same to get an ace the second time. Independent. Okay, last slide here. This would have fit better probably in our last section, but here we go. We want the probability of at least 2. And this is a terrible example. I got to change this slide, but at least 2, forget about the story here, just 2, 3, 4, or 5. At least 2 means I'm happy with 2, or 3, or 4, or 5. So I could add those up and divide them by the total number in the table. I don't know what it is here, 40, 50. So successes would be any of these 4 divided by the total. Well, you can do it that way if you want, but can you see that the opposite of this is just taking the 4 over the total? So if this is the opposite, let's just find the 4. Let's say this is, we got 30, that's 40. Okay, so let's say this is 4 over 40. Let's take the complement. Find the easier one and just take it away from 1. That was the idea of the complement that we talked about in our last lesson. So you can do these. You're going to get to the same place if you add these up and divide, or you could just find the other one, the other side of it, and take it away from 1. Okay, so when you tackle the worksheet, what you're going to see is one of these trees. It's going to be a story about, where's my tree? It's going to be a story about selecting cards. The first one, number 4. And so I'm going to get you started on that a little bit. You got green cards in this deck, and you have yellow cards. I want to write it up here. There are 5 green and 3 yellow. So there's 8 total cards. So the chance of getting a green is 5 out of 8. And a yellow is 3 out of 8. But then what you're going to do is you're going to grab another card. So you're going to grab card number 2. You're going to play the game twice. Now you're going to do this scenario 2 different ways. But the first time you put the card back in. So we're going to have, so we got a green card, we put it back. We're going down this road. We got a green, we put it back. Well, we still have 5/8 of a chance of grabbing a green. And a yellow on the second card is still 3 out of 8. And it would be true down here. Because we're putting the cards back, it doesn't change anything. So this column is round 1. This is round 2. You pick a second card, but these are all conditional probabilities. These are not and, these are conditional. And so what you do next, finish your chart by creating all the ands. Go up this one, and 2 greens, a green and a green, is 5/8 times 5/8. Go up green, go down the yellow. Chance of getting a green and a yellow is 5/8 times 3/8, and so on and so forth. Okay, that'll get you started on those. There's one where you replace the cards, and there's one where you don't. So give that a try, and let me know if you need a hand.